Light is fascinating. It's how we see the world. But what is light, really? For centuries, scientists debated its true nature. Some, like Isaac Newton, believed light was a stream of tiny particles. This theory explained reflection well, like a ball bouncing off a wall. However, other scientists like Christiaan Huygens argued that light behaves like a wave. This wave theory explained how light bends or diffracts around corners. Just like sound waves, light seemed to spread out. In the 20th century, quantum mechanics brought a twist. It showed that light acts as both a wave and a particle, called a photon. This duality is a fundamental concept in physics. Light can act like a wave, spreading out and interfering. But it can also behave like a particle, carrying energy in discrete packets. Understanding this dual nature is key to unlocking the mysteries of light and its many applications. From lasers to fiber optics, our modern world relies heavily on this strange and wonderful phenomenon. We've all seen our reflection in a mirror. This everyday phenomenon is due to the reflection of light. When light hits a smooth surface, it bounces back. This is governed by the law of reflection. This law states that the angle of incidence, the angle at which light hits the surface, is equal to the angle of reflection, the angle at which it bounces off. But reflection is more than just mirrors. It's why we see objects. Light from a source, like the sun or a lamp, bounces off objects and reaches our eyes. Our brains then process this information to create an image. An intriguing aspect of reflection is total internal reflection. When light travels from a denser medium to a less dense medium, like from water to air, it bends away from the normal. At a certain angle, called the critical angle, the light is reflected back into the denser medium. This principle is used in fiber optics to transmit light signals over long distances. Have you ever noticed that a straw in a glass of water appears bent? This optical illusion occurs due to the refraction of light. Refraction is the bending of light as it passes from one medium to another, for example, from air to water. This bending is caused by the change in the speed of light. Light travels slower in denser mediums. When light passes from a less dense to a denser medium, it bends towards the normal, an imaginary line perpendicular to the surface. Conversely, when light travels from a denser to a less dense medium, it bends away from the normal. The amount of bending depends on the refractive indices of the two mediums. Refractive index is a measure of how much a material can bend light. Refraction is responsible for many phenomena, like the formation of rainbows and the working of lenses in our eyes and cameras. Section 4. Light waves interacting, the dance of interference. Light, as we discussed, can behave like a wave, and just like waves in water, light waves can interact with each other. This interaction is called interference. The principle of superposition governs interference. It states that when two or more waves overlap, the resultant displacement at any point is the sum of the displacements of the individual waves. The most famous demonstration of interference is Young's double-slit experiment. In this experiment, light is shone through two closely spaced slits. Instead of seeing two bright spots on the screen behind the slits, we observe an interference pattern. This pattern consists of alternating bright and dark bands called fringes. These fringes arise from the constructive and destructive interference of light waves. When the waves from the two slits arrive at the screen in phase, meaning their crests and troughs are aligned, they reinforce each other, resulting in a bright fringe, which is constructive interference. When they arrive out of phase, where the crest of one wave coincides with the trough of the other, they cancel each other out, resulting in a dark fringe, known as destructive interference. Interference is a key concept in understanding the wave nature of light and has applications in various fields, including holography and interferometry. Section 5. Light waves spreading. Diffraction and its applications. We know that light travels in straight lines. However, light has a peculiar property of bending around obstacles and spreading out when passing through small openings. This phenomenon, called diffraction, is another piece of evidence supporting the wave nature of light. Diffraction can be observed in two main types: Fresnel diffraction and Fraunhofer diffraction. Fresnel diffraction occurs when the light source and the observation screen are at a finite distance from the diffracting obstacle. This type of diffraction results in complex diffraction patterns. Fraunhofer diffraction, on the other hand, occurs when the light source and the observation screen are effectively at an infinite distance from the diffracting obstacle. This is typically achieved using lenses. Fraunhofer diffraction patterns are simpler and easier to analyze. A diffraction grating is a device that exploits diffraction to separate light into its component wavelengths. It consists of a large number of closely spaced parallel slits. When light is incident on a diffraction grating, it produces a series of bright spots, each corresponding to a different wavelength. This principle is used in spectroscopy to analyze the composition of light from stars and other celestial objects.